A player kicks a football at a velocity of 12 meters per second from the ground at an angle of 30 degrees from the horizontal. Approximately how long will the ball stay in the air, and how far is the landing point from the kicking position? So, I'm going to start by writing our kinematic equations here. So we know that the displacement is equal to the initial velocity times the time plus 1/2 times the acceleration times the time squared. And the displacement is equal to the average of the initial and final velocities times the time. The final velocity is equal to the initial velocity plus the acceleration times the time. And the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. So here are the 4 equations that we can use. So since this is a symmetric, this is like a symmetric projectile, which means that its landing point is going to be at the same level as its starting point. So if I draw something like a line, pretend that's straight, but in a symmetric projectile, its starting point is the same position as the ending point, or the same vertical position. Its displacement in the x direction changes, which changes by the length r, or the range of the projectile. But when it lands, its vertical displacement is 0, so it does not change here. And because of this, in a projectile motion that is symmetric, and if there is no air resistance, it will reach its maximum height. So I'm going to say that it will reach its maximum height exactly at halfway through its motion. So this will take time t over 2 if there is no air resistance, since its maximum height occurs exactly halfway through its trajectory. So using that, we can actually use this equation to calculate the time it takes to get to this maximum height, and that will be half of the total time that it takes for this projectile to move across the field. So you can just use this equation. And we're going to be using everything in the y direction. So everything we will use will be in the y direction from here. So the y direction is the vertical direction, and the x direction is the horizontal direction. We're going to use the y direction. So we know that the y velocity, or the velocity in the vertical direction, is going to be 0 up here. So up here, the vertical velocity is going to be equal to 0, since the projectile stops moving upwards, and it's kind of like a turning point. It's like if you throw an object straight up, like straight up above you without any horizontal velocity, the object will go up, it will reach its maximum height, which is when its velocity stops, or velocity becomes 0, and then it will turn around and fall back down again. This turning point is when its velocity is equal to 0, and that will be the maximum height of your object. So we can apply the same thing in 2 dimensions. So the velocity, the vertical velocity at the maximum height is simply going to be 0. And that is equal to the initial velocity in the y direction plus the acceleration in the y direction, where the acceleration in the y direction is the negative of the gravitational acceleration, or minus g. So this becomes minus gt. Okay, and now we just need to solve for the time t, but we don't know what the initial velocity is yet. So if I draw this arrow as the initial velocity, where this is the launch angle theta, and this is the initial velocity, you can decompose this initial velocity into 2 component vectors, which are the horizontal initial velocity and the vertical initial velocity. So Vox, horizontal initial velocity, and Voy, the vertical initial velocity. Now, since the horizontal and vertical velocities are perpendicular to each other, that means they have a right angle between them, they can actually be broken down using trigonometry. So this becomes the initial velocity times the sine of theta, because sine theta is this velocity here over the initial velocity. And then you can just manipulate the equation. And same thing here, except this will be the initial velocity times the cosine of theta. Again, this is adjacent, and that is the hypotenuse, according to the angle theta. So that is our initial y velocity, which we can substitute back into this equation. So you can say that the initial, I'm going to move this over to this side here. So negative times the initial velocity times sine of theta is equal to the negative gravity, negative gt squared. So now this becomes positive, negatives cancel, and you get that the time it takes for it to reach half, I should probably specify that the time for half, or the time for the projectile to reach its maximum height, is going to be the initial velocity times the sine of theta, where theta is the launch angle, divided by 9.8, or divided by g, the gravitational acceleration. We're not going to plug in numbers just yet. So that's what we obtain for the time to get to the maximum height. But if you remember, the time for the maximum height is only half of the total time of flight in a symmetric projectile, where its final y position is the same as its initial y position. And then these two are equal. So let's call these y. They are both at the same y position. And what we've just calculated is half of the flight time of the projectile. So the total flight time, I'm just going to represent this as a lowercase t, is equal to 2 times the time it takes for the projectile to reach half of its height, which becomes t equals 2 times the initial velocity times the sine of theta, sine theta, divided by g, the gravitational acceleration. So we're just substituting that back in. Okay, I'm going to try to erase some of this. Okay. So now we can just plug everything in. So this is equal to 2 times the initial velocity of 12 meters per second times the sine of 30 degrees divided by g, or 9.8. Now, if you remember, the sine of 30 degrees is 1/2. So these two cancel out. And you get that it is equal to 12 over 9.8. So simplifying that, the time is equal to about 1.2 seconds. And I'm just going to leave it at that. So the time of flight is going to be 1.2 seconds. So I'm going to write that down. The total time of flight of the projectile is equal to 1.2 seconds. So that's the total flight time. Now we need to calculate the range of this football, or how far it will land from the initial position when it was kicked. So this time, we can use this first equation here, but in the x direction. Also note that we could also use this same equation to calculate the time by setting the y displacement to 0, because it's symmetric projectile. And we could have found the time that way, but that would have left you with a quadratic, and it probably would have been a little more tedious to solve. So now we just use that first equation, but in the x direction. So the displacement, or rather the range of the football, is equal to the velocity in the initial x velocity, or velocity in the horizontal direction, times the time interval. And we can completely ignore this second term, because there is no force accelerating the football in the x direction, horizontal direction. There's only the force of gravity accelerating it back down towards the earth. So this simply becomes the initial velocity in the x direction, which, if you remember when we decomposed, where this was theta, that's the initial velocity, was the initial velocity times the cosine of theta. So that's equal to the initial velocity times the cosine of theta times the time interval, or the time it took for the projectile to fly through this arc. So that is equal to the initial velocity of 12 meters per second times the cosine of 30 degrees. So I think a square root of 3 over 2, but I'm just going to plug it into a calculator, times the time of 1.2 seconds. Now this should give you about 12 meters. So I'm going to round it to two significant figures. So the range of the projectile is going to be about 12 meters. So it will land 12 meters away. And that is how you would solve this problem here.